Discover the future of mobility in our latest video, where we take you on a journey through the innovative world of electric vehicles. Uncover the high-tech components that power these machines and gain a comprehensive understanding of their operation. If you're intrigued by our content, please support us with a like and subscribe to our channel. For decades, fossil fuels have been the primary energy source for transportation. Yet, environmental concerns and the pressing threat of global warming are undeniably pushing us toward cleaner vehicle alternatives. Among these, electricity emerges as a standout, promising to revolutionize transportation's future. The advent and integration of new technologies in electric cars have led to a significant drop in prices and a notable increase in range. As a result, electric vehicles are rapidly evolving into formidable rivals to their internal combustion engine counterparts. Now, vehicles, whether they're fueled by gasoline or powered by electricity, share a common goal: converting energy to motion. But the fundamental principles underlying this energy transformation are distinct for each. In this introduction, we'll provide a quick overview of how both internal combustion engine vehicles and electric vehicles harness and convert energy to propel you down the road. This comparison will establish the foundational knowledge needed to understand the conversion of electrical energy into motion within an electric vehicle. To begin with, let's take a moment to understand the traditional internal combustion engine vehicle. It all starts when you fill the fuel tank with gasoline, a fossil fuel packed with chemical energy. This energy is directed to the heart of the vehicle, the engine, through the fuel injectors. Gasoline is precisely mixed with air and delivered into the engine cylinders, where it combusts to release energy, converting the stored chemical energy into thermal energy. The high-pressure gases produced during combustion exert force on the pistons, creating rotational force that turns the crankshaft. Subsequently, the transmission system engages, fine-tuning and directing this mechanical power to the drive axle, which then turns the wheels. Essentially, an ICE vehicle converts stored chemical energy into thermal energy, then into mechanical energy, which is finally translated into kinetic energy, enabling the wheels to move the vehicle forward. Electric vehicles operate through a unique procedure that significantly differs from their internal combustion engine counterpart. While the energy conversion may seem more straightforward because it involves electricity directly powering an electric motor, the process actually entails a complex pathway. This is due to the electrical input's nature and the battery's requirements, which require the input alternating current electricity to be converted to direct current to charge the battery. Then this DC power is inverted back to AC power to energize the electric motor. In the following section, we'll explore each of these components with detailed animations, providing you with an in-depth view of the sophisticated inner workings of electric vehicles. To truly understand how an electric vehicle functions, it's essential to walk through each section of the vehicle in the sequence it receives and processes electric energy. Our exploration starts with an intriguing companion, a single electron. This electron, or our electron companion, is pivotal in converting electrical power into mechanical energy. The journey of our electron starts by plugging the charging cable from the charging station into the electric vehicle's CCS. The CCS, or Combined Charging System, acts as a standardized universal interface for electric vehicles, seamlessly accommodating both AC and DC charging capabilities to streamline the charging process. This moment marks the beginning of the electron's voyage through the vehicle's electrical architecture. As we continue our journey, we encounter the Onboard Charging Unit, or OBC, tasked with the critical mission to convert AC to DC power, ensuring compatibility with the vehicle's battery system. Understanding how an OBC works might be challenging without first grasping the fundamentals of AC to DC conversion. Therefore, to provide a clearer understanding of the physics involved, we will cover the AC to DC power conversion concept with a familiar example: your cell phone charger. Imagine plugging your charger into a wall socket. What happens inside this small adapter is a simplified and miniaturized version of the onboard charger system. The AC power from your home's outlet is transformed into DC power, which is what is required for charging your phone's battery. Now, let's discover the brilliance behind AC to DC conversion through an engaging animation. A basic diode bridge circuit, widely used for rectification, employs three principal components to convert AC to DC: diodes, capacitors, and resistors. Diodes, designed to allow current to flow in only one direction, are pivotal in this configuration. This circuit features 4 diodes arranged in a specific bridge formation. When AC power is introduced, the diodes work in pairs to alternately direct the positive and negative parts of the AC waveform. This method transforms the alternating current, which changes direction periodically, into pulsating direct current that flows in a single direction, as illustrated in this graph. Integrating a capacitor into the circuit significantly reduces voltage and current fluctuations by releasing stored energy to smooth out voltage gaps, as shown in the highlighted graph. Furthermore, incorporating additional filters at the circuit's conclusion ensures a seamless DC output. As shown here, the addition of these filters changes the final output voltage from one with minor fluctuations to a consistent direct current. The illustrated process underscores the diode bridge circuit's effectiveness in providing a consistent DC supply. Now, let's expand this concept to our electric vehicle's OBC. The OBC undertakes a similar task but operates on a much larger and more complex scale. The process begins with AC input filters, including EMI filters and delta capacitors, components that mitigate electromagnetic interference and meticulously smooth out the electrical current. Next, the power undergoes power factor correction, a step that optimizes the electricity drawn from the power source by aligning the electrical current's phase with the voltage. Embedded within the PFC, we have the 3-phase boost converters, which elevate the voltage level of incoming AC power to meet the specific requirements for efficient DC conversion. The rectifiers then take center stage, performing the crucial task of converting AC into DC. Unlike a basic diode bridge used in simpler circuits, the OBC employs sophisticated power electronics such as silicon-controlled rectifiers, IGBTs, or MOSFETs for this operation. These components provide greater control, efficiency, and power handling capabilities, essential for managing the substantial energy flow required to charge an EV's battery. Additionally, a microcontroller, alongside sensors such as 6 current transformers, oversees the operation of these power electronics, precisely controlling the charging process to ensure optimal efficiency. Following rectification, the DC power might still exhibit ripples or fluctuations. To address this, the DC power is passed through additional filtering stages, ensuring it remains stable and consistent. Now, let's direct our focus to the heart of the vehicle's power system, the cylindrical battery packs. Each pack consists of multiple cylindrical battery cells which resemble the familiar AA batteries in shape, but are significantly more advanced and powerful. Imagine for a moment we could trace an electron as it navigates through the battery's interior. But first, let's peel back the layers of this metallic canister to reveal the secrets it holds within its core. At the core of electric vehicle batteries lie layers of anode, cathode, separator, and the electrolyte, each playing a pivotal role in energy storage and release. The journey begins at the anode, made from lithium, which serves as the starting point for our electrons' adventure. As the battery discharges, the anode releases electrons into the external circuit to power the vehicle, while lithium ions move through the electrolyte to the cathode. Opposite the anode we have the cathode, composed of materials like cobalt, nickel, or manganese, which gains lithium ions during the discharge process, completing the electrochemical circuit and enabling the flow of electric current. But what allows our lithium ions to move so freely between the anode and cathode while keeping electrons flowing through the external circuit? The answer lies in the separator, a porous material often made of polyolefin. It acts as a permeable barrier, enabling the transfer of lithium ions while keeping the electrodes apart to prevent short circuits. During the charging phase, lithium ions move back through the electrolyte from the cathode to the anode, storing energy by recombining with electrons at the anode. Conversely, during discharge, this process reverses. The lithium ions migrate to the cathode, releasing the stored energy and thus powering our electric vehicles through each cycle. Let's now transition from the physics of ions and electrons within the individual cells and elevate our perspective to the assembly level, where these cylindrical cells are grouped together to create a sophisticated high-voltage battery pack, or HV for short. Understanding the relationship between the individual cell voltage, and capacity in the total battery pack involves basic equations. When cells are connected in series, their voltages add up while the capacity in ampere-hours remains the same as that of a single cell. Conversely, when connected in parallel, the capacities add up, but the voltage remains the same as a single cell. Since Tesla is the main OEM using cylindrical battery packs, let's consider a real-world example by examining the Tesla Model Y for this particular EV. There are 4 sub-packs of high-voltage batteries, totaling 828 cylindrical cells. These cells are of the 4680 format, with a nominal voltage of 3.7 volt and a capacity of 22 ampere-hour. Given the complexity of the battery configuration, let's simplify the explanation. To achieve a 400-volt battery sub-pack, a series connection strategy is employed where the voltage of individual cells combines to total 400 volts. With each cell having a nominal voltage of 3.7 volt, connecting 104 cells in series would result in approximately 400 volt. Considering the Tesla Model Y, standard range requires a battery with an overall capacity of roughly 70 kilowatt-hour. Integrating the calculations into the total battery energy equation reveals that by parallel connecting 8 of these series-connected batteries, we can achieve the 70 kilowatt-hour total energy. This configuration ensures the system is balanced, achieving the desired voltage and capacity. While renowned EV manufacturers like Tesla predominantly utilize cylindrical cells in their high-voltage battery packs, it's important to note that not all OEMs follow this design. A frequently adopted alternative is the prismatic battery cell, which is favored by several automakers for its distinct shape and packaging efficiencies. Prismatic cells are battery cells with their chemical components enclosed in a durable metal casing shaped like a rectangular prism. This shape is particularly well suited for stacking multiple cells neatly to create a larger battery. Just as we demonstrated earlier with cylindrical lithium-ion batteries, the prismatic shell encases an anode, cathode, electrolyte, and porous separator, all sandwiched together. Despite their differing constructions, the operational principles closely mirror those of their cylindrical counterparts. Like their cylindrical counterparts, prismatic batteries can be interconnected in both series and parallel configurations, enabling the construction of a single high-voltage battery pack. Many vehicle models, including the BMW i7, Mercedes EQS, and Chevrolet Bolt, utilize prismatic cell batteries. For a generalized example, consider an EV equipped with 220 prismatic cells. Each cell delivers 3.7 volts and has a capacity of 145 ampere-hour. These cells are organized into 2 sub-packs, with each sub-pack consisting of 5 modules, and each module containing 22 prismatic cells. Each sub-pack is made up of 110 cells connected in series, yielding approximately 400 volt output with a total nominal capacity of 58 kilowatt-hour. When 2 such sub-packs are connected in parallel, the resulting battery pack maintains a voltage of 400 volts, while the capacity doubles to 116 kilowatt-hour. In this video, we have taken a deep dive into the complexities of CCS, onboard charging and battery packs in electric cars, exploring the crucial stages of energy conversion for storage in the EV. But our journey into the electric car's heart doesn't end here. Stay tuned as the next video will cover other essential components of electric cars, such as the inverter, transmission system, induction motor, regenerative braking system, and battery cooling system. Your engagement drives our content, so don't forget to hit subscribe and show your support by clicking the red heart. See you in the next video.